first of all. And I'm going to give a talk about AI reasoning and the inference time scaling. I guess it will be non-informal, so you can interrupt me and ask questions. Yeah, so first I have a question for you. Who likes beautiful presentations with clear highlights and descriptive figures? Raise your hands, please. This is not one of those. This is not one of those. It is far below my own standards, but sorry for it. I didn't have time to finish it. And I didn't want to move it again. Okay. Firstly, we will discuss limits of training time scaling, what was happening in the last 10 years. Then we'll discuss inference time scaling and like what is it and why I believe in it, for example. And then I'll go through state of the art in AI reasoning and the nearest future. About me, so I'm Ivan. Currently, I work at Together AI. We build infrastructure for other companies, so they rent our GPUs and whatever. I do training and fine-tuning inside Together AI. And before that, I launched a couple of mobile apps with AI characters with millions of installs that were in top 10 US Google Play. And before that, I was working as a research scientist at Yandex, where I was doing research around natural language processing, uncertainty estimation, and a bit of machine learning for physics. Do you hear me well, by the way? Super. Okay, so this figure describes what is training time scaling. This is what's happening since 2011 or 2014, depends on how you think about it. And basically, you have layers, neural networks, and someone who stacks more of them. So everyone talks about big models, like that they were growing for all this time, and like methods, theory-wise and like math-wise, methods didn't change too much since that time, but infrastructure and scale of what's happening changed significantly. How significantly? Yeah, so that's another illustration. What is training time scaling? So you have compute, data set size, and parameters of models, and you increase all of it throughout the last, like during the last 10 years, and test loss, which is reverse of quality, it was always significantly, like steadily going down. So that's just an illustration of what was happening, but this particular thing is from the scaling laws paper that was like a summarization of how we can make physical like scaling laws out of what was happening, whatever. Yeah, so if we think about the exact numbers, then in 2017, I remember when Attention is All You Need came out, it was something like 10 to the power of 7 tokens in the data set. It was translation data sets. 10 to the power of 8 parameters, and around 10 to the power of 17 flops for training. And in comparison, we have DeepSeek, which was released in December. This is V3, not R1. And it has 10 to 13 tokens, around 10 to 12 parameters, and around 10 to 24 flops. And so we can calculate that we have plus 6 orders of magnitude in dataset size. We have plus 4 orders of magnitude in terms of model size, and around plus 7. Yes, am I correct? Plus 7 orders of magnitude in terms of what compute we are able to spend for training. Then we can ask us then we can ask us a question: how we can scale it further, and if we can scale it further. So, and the answer would be that if we add all the data in the internet and other sources that we currently haven't added to the model training, including, like, for example, video data and multimodal data that is currently like used but not to the full extent in the foundational models, we will have +3 approximately orders of magnitude in terms of the data set size. We definitely can do +3 orders of magnitude in terms of model size. And I left the question sign in the flops because it is a question. I don't know, but hopefully we can scale it another like 5 to 6 orders of magnitude. Yes. Huh? It is a universal measure of computation, like how many, let's say, floating point operations you perform during training. Yes. Actually, GPU utilization during training is quite low usually. It's like 40% or something. So most of the time GPUs are just not working. Okay. So we have some estimates, but the important thing here is that this limit on the data is quite significant. So it is not clear, like it is possible to improve compute if we go further, but it is not clear how can we get more data further from this 10 to the power of 16. And also you can think of it that we added 6 orders of magnitude in the last 7 years, but it is not clear how will we add another like 6 of them. So we have saturation of data. We will possibly only like understand how to add 3 orders of magnitude here. And yes, so in terms of data to further, so we will have a limit with the internet data that we currently have. And then we need some mechanisms to gather more data. And two mostly discussed approaches here are agents. But if you take an agent and put it in the real world environment to get not internet but real world data, then you need to wait real world time to get this data. So you will have science style experiments that you need to conduct, which are very slow. And this data gathering mechanism will also presumably be very slow. And the second approach is synthetic data. There are many good papers that show how you can use synthetic data to improve quality on something that the model already can do, but needs more examples to generalize or to better understand the task or something like this. So it is not, there are good ways to generate and use synthetic data for something that is in the main for the model that we already have data on, and we need to just, you know, tweak it and change it a bit to close the gaps in model abilities inside what it already can do, like small local optimization. We can think of it that way. And It is actually very hard to generate synthetic data with which you will be able to gain new knowledge. And I don't know of any good research in this direction, what I would consider good. Then there is a problem of memorization vs generalization. So first statement, that memorization is not knowledge extraction and it is not knowledge understanding, meaning that if we see that the model can copy paste various amounts of data from the train set, it doesn't mean that it actually understands anything from this data. And memorization is basically the objective of what large language models and similar models are learning now. We're teaching them with this objective. And they are good in it because we optimize them well for it. But then if we dig a little deeper in the knowledge aspects of what's happening, then we will have some interesting discoveries. And firstly, we, for example, can think about knowledge extraction. So the very simple example task is that given a person's biography, extract a year of birth. Yes, so just you have some biography, some year of birth, you have some of this data in the trained data set, and then you give some other persons with different set of parameters but the same template, and you ask like GPT-3, for example, not the latest models because they already optimized for it, but like something that was not specially optimized for it, and ask it to extract some particular data out of it, like the year of birth or full date of birth, like, or some. This is a very simple example, but the idea is like that. And it turns out that by default, such task doesn't work for any out-of-domain data. So you can think that if the model outputs you some information about, I don't know, solving of a mathematical equation, then it understands each step, but actually it does not. So if you ask it like to even to extract some particular property of the data that is written in the thing that it probably can generate, but out of domain. So it's a good definition how far from your pre-training domain you should be to see this behavior. But the general pattern is that it does not understand how to extract knowledge, so how to decompose input into the graph, let's say, yes, so into some aspects. If you tweak the data slightly out of the main pre-training domain, so add some tokens that it didn't see in the training set, or in terms of biographies, I don't know, add Chinese names in the beginning of the biography, and for example, it will not work. And in order for it to start working in the pre-training, you need to add 3 orders of magnitude more data for this particular template. So it is like some numbers of data that you need to do to make a model actually understand how to extract knowledge, to divide the input into knowledge pieces that can be extracted. Does it make sense? Like, okay, by the way, as I mentioned, slides are not well prepared, so you can ask me questions as I go through the presentation. Yeah.
Hello. So here you mentioned augmented data, right? Like, I mean, generally, in like basically from text data. So would it work like doing some level of entity extraction from data and like structuring line for like categorizing dates and important information in each thing, just to like give it and then training the data with this augmented data to be able to like extract these dates? Is that what you mean?
I mean that, okay, you have some training examples of biographies, for example, in your training set. In order for the model to be able to extract particular parts of the biography with your request later, for any person, not persons that you see on training, you need to have at least like that's a good question, because I didn't add what is the baseline data in this experiment. But the point is that you need to have at least 1,000. Yes, so here at least 1,000 different variations of the properties that you are going to extract. Yeah, so the proxy for this statement is that sorry. If you have 1,000 variations for a particular parameter, then the model will be able to understand that this is actually a parameter, and will have some special property inside its working process to mark this as a parameter and then be able to extract it.
So
is it a good answer or no?
It's similar to how we do it in prompt engineering, where we give it a few examples of prompts and the specific answers that we require, so that the next time when somebody gives him that prompt, he gives the answer that is actually needed, right?
Sorry, I didn't get the question.
So in prompt engineering, we prompt the ChatGPT API to look at these kinds of prompts, and if you get these kinds of prompts, you have to give these kinds of answers. So is it the same thing with this, with knowledge extraction, where we train the model to...
No. The difference is that you need to put this in the training, not in the prompt. To the data that model sees during pre-training when they train it.
Yeah, but they're similar, right? The end goal is still knowledge extraction.
Model behavior is very different. Like in terms of knowledge manipulation and work with knowledge, pre-training and post-training is very different. Like if you, again, so if you have some, like, it's hard to make general statements here. But example here is that you put, again, you trained on Europe, like Latin names, yes, and then you have a Chinese person in the biography. And the model understands Chinese language, but it wasn't trained for Chinese biographies, like specifically special data set with biographies. Then if you add, I don't know, 1,000 examples of various non-Latin biographies to the data set excluding Chinese, for example, then it will work with Chinese. And if you do it in the prompt, I'm not sure if it will work. Maybe it work. Maybe it will work, maybe not. I don't know. It depends on the model. But this is like a general statement that you need to have at least 1,000 variations for a parameter. And it adds 3 orders of magnitude to the data requirements. Yeah.
So say, for example, I want to know exact date of birth of a specific author in a biography which has been given. Because the date of birth from like a Chinese room analogy, the date of birth is not understood by the model. But if we say born on, so we give variations of asking the same questions as well as parameters. At the same time, previously have confirmed when the data was being trained that when a statement like this comes, you break it down that, say, Sheldon Cooper, born in 1924, is a mathematician. Same statement can be, a mathematician named Sheldon Cooper was born in 1924. The 1924 was an exciting year because Sheldon Cooper was born in this year. So multiple variations of the same statement have to be trained as well, because the concept of understanding doesn't exist? Can that be an example of what you're saying when we say
Understanding is a different thing. Currently, we talk only about knowledge extraction. That if you ask, like you have a biography of Sheldon Cooper, and you ask when Sheldon Cooper was born, given. So you give in the biography in your sentence, in your prompt, and then ask and give me date of birth of Sheldon Cooper. If Sheldon Cooper is close to the biographies present in training data, it will work. But if you have, for example, things, a Chinese person and the rest of the biography written in English, but with Chinese name, it will not work if you didn't add these variations to the training data. So it basically tells you that even knowledge understanding is much more complex than this. To just flag that something is a parameter and some like that there is some retrieval kind of meaning for a parameter, so that model can understand that this thing relates to this and I need to output it. Like it is a very simple operation. To retrieve knowledge from a given data, you need to add these 1,000 variations. Did I answer your question?
I think yes. I think I'll understand better as we go further and you come into understanding of it.
Okay. Okay, let's go. Next, we have knowledge manipulation. So then knowledge manipulation means that you first extract this knowledge and then you ask the model to do something with it, meaning that it understands what it actually extracted. So the simplest example here is, again, you have a biography and you ask, like, was name, some person, born in an even month. So it is the very simple knowledge operation. And it turns out that these tasks models cannot do without a chain of thought, for example. So there is no, probably even with the current best models, I don't. So these experiments were like not in the. They were in a highly controlled environment to make some general statements about what models can do and what they can't do and how it scales. So we are now exploring the limits of pre-training. So pre-training gives you a model that outputs you some tokens. And for example, it turns out that doesn't matter how long you pre-train the model, it will not be able to output the exact answer without the chain of thought. So without some reasoning process during the generation phase. What?
So in the previous slide, the content that you mentioned, it was in the training period, right? And the prompts were below.
What was in the training period?
So the biography of any individuals, is this, this is in the training, this is provided in the training period?
Yes.
Okay.
Yes. So yes, so we covered this knowledge extraction, and then there is knowledge manipulation. So we are slightly going towards what is understanding. Yes, and manipulation means that, okay, you extracted the date of birth. Can you now tell is it an even number or not, or odd number? And it turns out that without explicit chain of thought, models cannot tell if the number is odd or even. So you've given some data to the model, and in order to manipulate it, it first needs to write it. It cannot remember it in its internal states. Does it make sense? During pre-training. chain of thought means that you allow the model to explicitly write some sentence or explicitly write this number during the generation. Yes. So it's an interesting statement here because it is a limit of what the model can do on its these internal states, mental states that we don't understand. So turns out not much. It needs to explicitly write the reasoning to do even such simple operation.
Prompts itself again with that second question, and then it gets the answer to.
If I remember the experiment correctly, yes.
Right, so it prompts itself with the new context. This is the month, yes. And then it's so that's what happens.
Yeah, I will.
But by the way, this question you can ask to like ChatGPT and Claude and see if they will work without chain of thought. Yeah, so now the statement is that LLMs need a whiteboard. So there is no whiteboard inside the internal states, inside the parameters and the inner process of working. And this also gives us ability to check the reasoning process. So if we didn't change the architecture and we still work with the same transformers, it is a like hard constraint. People will always see the reasoning process. Then the next thing is knowledge capacity. So there are a bunch of papers that have approximately the same conclusion, that LLMs can store up to 2 bits per param of knowledge. And knowledge here means like mathematical meaning, like entropy. Information theory definition, information theoretic definition of information. Wow. Yes, what does it mean? It means that if you take a DeepSeek size of model, which is currently the best open source model, and it has approximately the same size as GPT, as OpenAI closed models, and as Google, it is less than 1 order of magnitude difference. And then you compute how much this uncompressible knowledge it has. It turns out that this is approximately 1 terabyte of data, 10 to the power of 12. Yes, but I also mentioned that previously that you need 1,000 examples in the training data to achieve. No, it's a different statement. Sorry. But you need at least 1,000 repetitions of the same thing in the training data to achieve this effectiveness. And any junk data harms this by 1 order of magnitude. So, interesting number. What can we say about it? Well, for example, in Hadron Collider, one launch of an experiment is petabytes of data. So it's 6 orders of magnitude difference. It is more. It is 6 orders of magnitude more than what current LLMs can theoretically remember in their states. So it means that with current LLMs, we'll always need a database to retrieve from which. It is also like interesting, it is general statement. They will not be able to remember experiments and then do some magic with them. They will not be able to even read all this data, like read and remember, okay, whatever. Yeah, so statement about the database. So we have limits on what the model can actually remember too during training. Does it make sense? And these limits are pretty tangible. It's just 1 terabyte. It's like any hard drive that you have. But it is, it must be a very high entropy thing, so you cannot compress it.
Does it compress it?
um,
Should be able to compress it after each compute, no? Like for example, you're doing like series of conversations with certain model, then does it compress it after each cycle?
could you elaborate on the question? I didn't understand. Like, yes, machine learning models in generally compress information a lot. Here I mean that there are some information sources that you cannot compress. For example, a Hadron Collider. It is very hard to compress information. And I mean that in nature, I wanted to show that in nature there are observations that are much more complex than what biggest LLMs can potentially remember, theoretically. Yeah, so we have limits on this side too, on what's happening. I also added this question here on what do LLMs actually understand and what do we understand. I added them just, you know, kind of philosophical questions. Because so I mentioned several like knowledge capacity extraction and manipulation, and we saw that there are limits there on what this pre-training models can and cannot do. And then there is a much harder question on what do they actually understand. And I would say that currently there are some good works that show that there is a generalization in quite hard domains, for example in math, and we will discuss it a bit later. And it means that we cannot distinguish if the model has understanding or not in this domain. So for us, it looks perfectly, verifiably like understanding, like a sentient thinking. But what's actually happening is a much harder question. Yes, I guess the main reason for this slide is just to say that while there is some work towards generalization and understanding, the actual definition of understanding in LLMs is very hard, as the definition in humans. Another problem with pre-training is that pre-training is long and requires tremendous amounts of data. And you have some methods that do work with small amounts of data compared to the original training set, like mostly like fine-tuning and variations of fine-tuning, and you can also do reinforcement learning on top of it. And one of the main problems with the knowledge is that you need to adapt for the changing environments, and currently there are no good training methods that actually can do it, because pre-training is too long and too data hungry. Fine-tuning does not really add understanding. It memorizes the data that you provided and maybe gives you some domain adaptation, but doesn't work for generalization. And about relay, I will talk a bit later. So yeah, we discussed that we have limits on pre-training from the biggest and the most important is from the data perspective. We also have compute, and compute translates to energy. And we also have knowledge, all the questions regarding knowledge, but we also have very basic questions regarding manipulation and knowledge capacity. And there are no good adaptation methods right now, at least of which I am aware of. Yes, so now let's talk about the inference time scaling. So from the previous section, remember that the main idea was that in the last 10, 15 years, we were scaling compute and data in the pre-training stage. inference time scaling actually tries to scale quality and compute on the inference time. So I mentioned the chain of thoughts. Chain of thoughts is this thing that the models output then when they say they are thinking, basically, or when you allow them to, when you ask them to think step by step. And it is an iterative generation process where you want the model to increase the quality of output with the number of, with the amount of compute and the length of the sentence that it already generated. Yes. I think we can discuss it a bit later after the next slides. But the main examples of thinking models is O1, O3, and R1. And that's what these companies are trying to do now. They are trying to make models correct their errors and kind of explore the current problem and build some understanding on top of, like in real time, on top of which you can make some assumptions and statements and correct your mistakes. And there are several challenges in this process right now, but currently we have slightly, I would say, we have hope for a better curve, better slope of what we gain based relative to the amount of compute that we put as an effort. So it is much faster than gathering data for training and changing your model parameters, essentially. There is also this system 1 versus system 2 analogy that system 1 is more like a scaling of compute, and it is also more like whatever a human can do in a slow amount of time, our emotions, our autonomous processing, and everything fast. This is what pre-training can do. But in order to make some long-term long-term logical reasoning, you need to have some slow processes and build this understanding during your inference time. Yes, as I mentioned, the main target with inference time scaling is to have a better slope of scaling and also to solve all the problems that I mentioned for the pre-training stage. Yeah, so currently I'll talk a bit about what is the state of the art in reasoning and in inference time scaling right now, and then let's make a small QA. Where is the image? Oh, I don't see it. Okay, whatever. It is here, but not here. Okay, I guess many people already know about the reinforcement learning because it is as a part of AI very hyped in the recent years. But the basic idea is that instead of preparing your data for the model, you prepare the environment where the model can explore, collect data by itself, update its exploration and exploitation policies, and improve quality in this environment. Yes, so you have environment, a model that takes action, rewards that environment gives to the model, and based on these rewards and observations from the environment, model improves its policy, its actions. Yes?
So, how does it create a trade-off between understanding and compute in reinforcement learning? Does it look into that at all?
you can interpret humans as someone who does reinforcement learning, in a sense, because like we learn the world this way. Yes, so in neuroscience, for example, if you think about, if you read about state-of-the-art models of our own world understanding, you will have similar formulas that you have in reinforcement learning.
But is the system trying to optimize for compute or understanding in reinforcement learning is the question? Because it'll optimize, it is learning, but to it doesn't matter how much compute this takes, because it will impact its.
Yeah. By the way, that's. Thank you. I forgot one of the statements I wanted to tell here. So, what is scaling of compute? This is scaling of understanding. So, if you think about it, we as humans gain a lot of. We became much smarter in the recent 2,000 years, but our compute, like our brain power, didn't scale at all. So something else scaled, and this something else is our methods on how we apply our compute. And that's what I mentioned as a scaling of understanding on this slide. Answering your question, in reinforcement learning, you optimize to predict the world better. Like the ultimate target is that you are trying to predict environment reaction on your actions. It's also there is a funny interpretation for this. So related to psychology, you can optimize your understanding of the environment either by actively exploring, taking some pain based on the environment reaction to your actions, and then correcting your world model of how you understand this environment. So explore. Or you can just sit on one place and do nothing, and you will also perfectly predict the environment because nothing changes, you don't try anything.
Does the temperature of the model change the way it would behave? Would it change its action to the environment?
You have a, so here is an example with a mouse. Like the mouse learns to search the labyrinth, and it doesn't know where the cheese is hidden, and it doesn't know the structure of the labyrinth. But as it explores the labyrinth, it understands which paths are not correct and doesn't explore them second time. That's learning. That's why it is here. That's a simple example. Does it make sense? Did I answer your question? Ask it again. Okay. Okay, so now I will tell a couple of words about free models. First of which is a DeepSeek R1. And most of the advancements in DeepSeek R1 are actually in the very low near hardware optimizations. But one related to the reasoning and important one is that they are the first one who showed that you can do this reinforcement learning without modeling the reward. So they took, usually you use, in reinforcement learning you use several models at the same time. And usually you have a model that explicitly tries to learn the environment and predict rewards based on actual environment observations. And in DeepSeek they showed that you can remove this model, you can just take the LLM and the environment rewards, and the current LLM are so good that you can just allow them to explore by themselves without complex reward modeling, and it will still work. And it will not only work, but it will show you some emergent capabilities in these models. And in terms of, in DeepSeek, it was emergent error correction. So with chain of thought, people usually put explicit like asks for the model that you need to correct your behavior, check for errors. They try to build some special functions to do this, but in DeepSeek, there is nothing like this. They just gave an environment, take a pre-trained DeepSeek V3 LLM, and set up the loss function that works with the environment rewards. So it is a bit technical detail, but the most interesting, like, without technical details, is that the models can actually have emergent error correction behavior, and error correction is necessary for this chain of thought long thinking without human supervision. So if models are exploring the world and just giving and just observing their rewards in mathematical tasks, they will stop themselves and tell themselves like, stop, I need to think more, I need to verify this, and so on. That's fun. Yes.
This reinforcement learning, the error correction, it learns it in pre-training, and the model itself has this capacity. Or do I understand wrong?
Technically, it's post-training, but no, you take the pre-trained DeepSeek V3, a big model, and then you do RL on top of it.
What does that mean?
It means that, okay, you have a model that speaks good, like ChatGPT, and then you want it to solve international math Olympiad level tasks. It will not do it. You set up an environment that gives you rewards for correct answers. That's it. So you tell, okay, the model, this is the answer, and if it is correct, I tell you that it is correct. And that's it. Like, if you set up such an environment, it turns out that the model will be able to convert itself from this chatting bot to mathematical Olympiads bot. And yeah, so I said previously it was always guided chain of thought in all other models. They trained it to, they explicitly like wrote a special code that checks if if something is correct, and then asked the model to like there was some human input, let's say, during the generation procedure that helped the model to self-correct. But here, in a sense, model understood that it doesn't understand everything. Yes. So it understood that it makes errors, and in order to make less errors, it needs to verify what it already said.
So you have the base model with all the weights, that stays the same. Then you have some new database that allows it for better chain of thought, some new model. Is that also weights, or how is that represented, this emergent error correction?
No, it's...
Okay, I'm going to do my stand-up comedy show and try describe the whole problem. Okay, generally think of LLMs as a metrics, right? So essentially, everybody understands matrices, right? So multi-dimensional matrix. So effectively, when it's being trained, there's a value that's put there. It's not going to change. What he was trying really hard to explain to everybody is like, when it's trained, when new data comes in, the state update function is not really learning itself by looking at what is being said and the feedback loop being incorporated into the learning. And that's what it does. So imagine this to be an LLM traveling through time and learning as it goes along. Yes, in a loose sense of speaking, yes. Absolutely. Oh, sorry. Comedy show over.
Could you give a...
Yeah, thanks for this, but my question is not related to any of these, but like a little bit more generic. So our very own existence proves that we can have models which are much more efficient. So what is the current state of the art, or anybody else who's trying to replicate this? Because if you look at it, I think human beings are good at developing certain types of things, whereas our evolution was good at developing certain type of things, right? If you look at the nanotechnology that we have inside our own bodies, which has developed through evolution, is way more efficient. But at the same time, that evolution did not give rise to, say, faster travel or something like that. So we are good at that, right? We invented air travel, but our understanding of nanotechnology today is nowhere near what nature can do. So there's this clear mismatch about what our intelligence is able to do versus what evolution did. So is there a way we can, think about developing our own brains in that sense, that doesn't require so much compute?
What is the actual question? So we have evolution, sorry. We have evolutional optimization, and we have our custom optimization based on our knowledge.
Right.
And what's the question?
My question is, can we create intelligences which requires, say, is as efficient as our human brains currently?
I think we surely possibly can.
Possibly can?
Yes, sure.
Okay.
In this the very first table here, maybe I. Here we can add a brain, and for a brain, the model size will be something like 100 trillion parameters. It is 10 to the power of what? 14. Yeah, so in my nearest future, we will have the same model size as brain, so similar, maybe one order of magnitude more. But we will not have nearly the same efficiency in terms of knowledge, manipulation, or energy. Did you mention this? Did you mean this or no? Or like, and we. So problems that I mentioned that they are not. I am not answering your question. What is the exact question?
No, we can take it offline.
Okay. Yeah, so in the nearest future, we will have same number of parameters as the brain. Currently, we are 2 orders of magnitude low. Okay. This is about DeepSeek. About AlphaZero and Alpha Geometry, interesting things are that they also do, in a sense, AlphaZero is the first really impressive inference time scaling. It was because I wrote these things for the alpha geometry, but whatever. Actually, you have some paths over which you sample. And for AlphaZero, it is this Go or chess predictions of the next moves. For alpha geometry, it is formal logic. Like you have an mathematical engine that samples correct paths. And then you need to train a good reward model that will assign weights to this hypothesis and rank them. And this way you will have this exploration and error correction. You will have exploration, but not error correction. So interesting thing here is that both of these approaches and also the stuff that people do in biology, but I'm not that expert in them. They always sample verifiably correct paths, and then they just rank them. So they always operate within these environments where you don't have to do error correction, and they actually gain the understanding of what's happening. You have this pre-trained model that can very fastly kind of intuitively tell what to explore, but it is not able to actually construct the good paths for the exploration. Yes. So I mentioned it that these are the good examples of inference time scaling, but they have this problem that they work only in the very controlled environments. And they don't actually solve all the problems that I mentioned. And the last model that I wanted to mention is S1. It is like full open source model for the inference time scaling, and they have nice figures that shows what it looks like and what do we want to have in the future. So right x-axis is horizontal axis is number of tokens during the generation, and vertical axis is accuracy on the given task. The middle task, for example, is a competition math, AI, whatever. And what we want to have with inference time scaling, that we always have this linear dependency, that with improved thinking time, we'll have improved accuracy. And for all the models, currently there is a saturation of this. They cannot think for significantly longer periods than was in their training data, which is typically something in tens of thousands of tokens. And this is a significant barrier to solve. But with these models, you can actually experiment. They are open source Qwen models tuned for math competitions. Yes, so with inference time scaling, currently we have this problem of adaptation, fast updates, and efficient learning. We have context length limitation, and we don't have any good idea on how to build error correction based on the understanding of things and not on random exploration with RL. Yes, so that's it for the slides. Now questions.
Thank you. So in the beginning of the presentation also you mentioned that models do correction real time, like they not when we talked about R1 but much earlier, that they do correction, so hence they will go through a logical process and then be like, wait, hang on, this is not correct, and then they'll correct themselves. But earlier, when, at what time, like before it was doing emergent error correction, how, like, was it coded within it, like you need to do error correction now, or was it another agent coming and telling it, like how was it embedded in the thinking process?
What part, what slide do you mean?
Wait.
Huh?
After this. After this. After this. After this. I think over here you had mentioned about error correction.
The difference is that whether you have understanding of what is an error. So RL, reinforcement learning theoretically doesn't have limits on what it potentially can optimize. But if you talk about reinforcement learning in the highly non-verifiable random environments, you need, like, it is very hard to construct a good reward function that will actually tell you how far are you to the solution, how far are you from the solution. And in a sense, okay, let me think a bit to answer your question and not some random question. R1 uses reinforcement learning, but without, so it is still reinforcement learning, but without the reward modeling by us. So it is just the environment signal from verifiable environments like math or code. So DeepSeek R1 uses reinforcement learning. Is it an answer?
So it is fine-tuning. It's fine-tuning itself. No.
It's not what is called fine-tuning in the community. So by fine-tuning, you usually mean that you do the same thing as the initial pre-training. So you predict the next token or some advanced variations of this, but you do the same thing, the same loss function on the new data. That's fine-tuning. And reinforcement learning, it is completely different environment, and completely different loss. And it is not supervised in the sense that you don't have a you don't have a loss function for all the data that the model outputs. So it just outputs something. You don't have data on which you are training it. You just give it environment. It outputs something. For this something, you generate a reward. And if you have verifiable environment, it is easy to compute this reward. This is just if the answer is correct or no. And then, based on this answer, it updates its generation process.
And when you say update generation process, you mean updating the model weights?
Yes.
And that's how it becomes like an Olympiad.
What was the worst slide? The worst of this of these bad slides. Yes. What was the painting?
Yeah, I have a question.
Yeah.
Yeah, I have a question. So initially you mentioned certain types of like pre-training, fine-tuning, and reinforcement learning, right? For a model to, let's say, update itself, there is, I believe, another method called continued pre-training. Can you elaborate a little bit more on continued pre-training, and is it like a good idea to improve the database of the original models? As opposed to, I mean, reinforcement learning, I know it's based on like taking actions and through chain of thought.
It works with the weights
Yeah.
of the model too. Continual pre-training again. So the main problem with all of this discussion of RLVC pre-training or pre-training VC inference time scaling is that during pre-training you do memorization, and in order to do anything except of memorization, you need to like have very good coverage of particular variables that you want to work with. Like, and this means that like you need like to be sentient about all things that current models do. They need like 3 orders of magnitude more data in the same domain, not some new video whatever.
My angle was mainly concerning personalization of a model, like personalization, mainly how a user will be using a particular model, let's say for a longer time, for work or whatever, and the way the model would update itself about the user to like serve the user better. So my question was mainly around, these are the two approaches where in one way it would improve its actions and decision making and reasoning, and another way it would update its existing knowledge base while it's serving the user. So my question mainly was asking whether continued training is generally is it an inefficient method of approaching this problem, or there is any kind of merit to this method for expanding the knowledge base, mainly personalization?
Continual pre-training works good if you need to memorize more. So that's the main use case that I see. I don't. Quality-wise, from my experience, if you want to adapt a model for some not easily understandable preferences of humans, you need preference tuning. So the original preference tuning was with the reinforcement learning, as OpenAI did it. But currently you have RL for poor people. So essentially you have preference tuning that works similar to reinforcement learning, but you only need to sample to have these preference pairs and not the environment. And it works good if you want to optimize your chat model for a particular psychotype of your clients, for example. And from my experience, this preference tuning or RL does give significant improvement, while fine-tuning efforts do not. Okay. Another question.
Is it similar to the Google Titans paper that recently came out? So there was a paper from Google Titans where they are doing something similar, where the model weights are allowed to be altered based on the initial prompt.
Could you repeat the last part?
Yeah. So hello. So basically, there was a recent paper by Google Titans. Google paper, the name was Titans. So there, I think it was similar to something where the model weights are allowed to be altered based on the user's prompt. So that was probably in January or December.
Weights were allowed to
be altered. Some of the weights
altered.
Yeah.
All of the models alter their weights now, I guess, because it is much more efficient for during the training. So DeepSeek has 32.
No, I mean after the training, like during when the user is using them, let's say, from using the prompt will allow the weights to get altered as well. Some of the weights on the end layers, something like that. I think. I am not sure. I didn't go through the whole paper, but I went through a summarized version.
I remember the name. I don't remember the content, but for sure you can alter weights based on prompt. You can have as I mentioned, the most important alternation of weights happening because currently all of the models are a mixture of. Okay, all of the models are a mixture of experts now, no, I fixed it. Thanks, Chuck. All of the models are a mixture of experts now, and during the generation there is inside the model a classifier that decides which part of the model to activate. And all other models, they can be in a different nodes, and they are not activated. And it is very efficient because different models stores different information. It memorizes different information, essentially, and different code that it learned to execute. And during the generation, if you have a prompt, you can vary. You always have this variation of experts, but you can also vary adapters. So if, for example, you have different parts, adapters that tuned for different tasks, and then you decide which one to activate. It is also common. But I don't know exactly what Google did in that paper. I don't remember it. I have time, but I think we should wrap up.